We'll just put the book there, just in case you're wondering what the book we're using here. Now, that's what you did in the first lab. Go into the lab, we probably gave you 10 resistors and saying, can you tell me what the value of the resistor? And basically what you did is going by that. We have 3 bands on the resistor. Sometimes you have 4 bands, and the last one at the end here, that's your tolerance there. So based on the color, which is, I could never read them, I'm colorblind almost. But let's say you have red, green, and blue. You go red, that's 2. Green is 5, so that's 25 so far, the first 2. Then you look at the blue, which is your multiplier, the third one. What's blue? 6. So that's your multiplier. So you take the first one, you take the second one, and write the number of zeros indicated by the multiplier, 6, 0. So it will be what? 25, 0, 0, 0, 0, 0, which is what? 25 million ohms, mega ohms. Now the tolerance is the percentage. If it's gold, the value should be within 5%. If it's silver, within 10%. And if none, if you don't see anything, you get a cheap resistor within 25. You know. So that's really how you calculate the value of each resistor. The multiplier is 10 to the power. If it's green, 10 to the power of 5. If it's yellow, 10 to the power of 4. Or just take the 2 numbers. Let's say now it's brown and yellow. Brown and yellow, what's brown? 1. Yellow is 4. That's 14. Then if the third one is red, you add 2 zeros. 1400. Or 10 to the power of 2. That's 100. That's 1400 ohms. Plus or minus based on that band there. If it's gold, it's 5%. Those are the good ones. Silver is within 10%. And again, if you don't see an extra one there, your resistor can be off by 20%, either plus or minus. So I think in the lab you took 10 of them, you read the values, then you measured them, and hopefully they fit within that tolerance. Did they work in the lab when you did them yesterday? Yep. Okay. So that's what it was. Yeah. And I don't know what you're going to be doing in the lab. As I said, I don't do the lab. Somebody else does the lab, and she goes through the stuff. Today we're going to be talking about voltage sources. We talked about resistors last time. We talked about not capacitors, not yet. We talked about voltages, currents, charges, SI units. So today we're going to talk about independent and dependent voltage source, independent, dependent current source. How do we draw them? And then we'll do some examples with little circuits there. Then maybe we'll hit Ohm's law and power here. We'll talk about power. That's why I could never, actually, I look at these and I can't tell the color on the resistors here, especially when they're really small. But I don't know if that's a blue, red. I don't know if there's a blue here, or I can't even see it. There's a blue, red, and I couldn't tell you what the last one is. So I always go, never mind, I just plug them in, measure the value, you know. So let's look at an independent voltage source. Independent voltage source. And the way we draw independent voltage source, we usually draw them like this. It's a voltage source, so it's plus to minus, and we put the value of that. Let's say this is 10 volts. That means this source will always give you 10 volts right here between this end and that end, regardless what you attach to that. If you attach a 1 ohm resistor or complicated circuit, this source will always give you 10 volts right here. It doesn't matter what's attached to it. So sometimes you see me go like this, and I go, there's a circuit here. And I don't care what that circuit is. This source is supplying 10 volts to that one, to that circuit. That's an independent voltage source. Now some people will draw that by going like this too, like a battery. 10 volts. That's what we use for a battery. Oh, is that yours? Okay, I wasn't sure. Like, that's a 10 volts. Again, what that means, when you look at that, that this end, because the plus on the top, the minus here, this end is 10 volts higher than this. That's the same thing. this end is 10 volts higher than this. I don't want you to think this is 0 and that's 10. It could be. If I attach this to ground, then yes, that is 10 volts. But if I have a source like this, independent source, and for some reason this end is not attached to ground, is attached to negative 5 volts, and this is 10 volts, what's the voltage right here? It's 10 higher than this. What's 10 higher than negative 5? 5 volts, the voltage on the top. So a mistake, people think it's always 10 volts on the top. Not really, it depends what we have attached right here. Most of the problems you're going to see in this class, you'll see me attach the ground to the bottom line. So if I attach the ground to the bottom, that is a 10 volts. But if I have a circuit that looks like this, that's plus here, I made it too big here. I have 10 volts, bless you, and this is a resistor, and I attach the ground here. Now that value is not 10, because it's going to be some current going through that, and it's going to mark this plus to minus like this. So there's going to be a value here, a voltage here. We'll call the voltage Vx, and this end is going to be what? 10 plus Vx. Now I don't know if Vx is positive or negative. I don't even have to tell you if it's going up or down. We have to calculate that, but there's going to be some current going through that. This is a 0 volt right here. That's a 0. This is going to be Vx, could be a plus 5, minus 2, could be any number, and that end is going to be 10 higher than this value. If I take that resistor out and slide it down there and put the ground here, then that value is 10 volts. So what about a current source, independent current source? It's a current, so we draw an arrow for that. We go, that's an independent current source of 2 amps. Now, that means this source will always push up in this direction. I drew it up, 10 amps up in that direction. So what is the current going this way? It better be 2 amps. So this is my circuit here. But that source is going to push up, going up. There's no other way to exit. It's going to go in that direction. 2 amps go in that direction, regardless what's attached to it. I might draw it pointing down, as I have a current source pushing down of 3 amps. That means there's 3 amps going in that direction all the time, regardless where you attach right here. That's the way we draw an independent current source. So we know the independent sources. Let's look at the dependent sources. There's a dependent voltage source. There's a dependent current source. In a few minutes, we'll start doing circuits with all these pictures in it, so you have to know what each one is. So dependent current source. I might draw a picture like this. First, a dependent source will look, the shape will look like that. Since it's a current source, it's going to have an arrow going through it. That's dependent current source. And I might have a problem like this. I'm just trying to make the circle a bit bigger there. And let's say I have that problem there. So what you might see me label this current as I sub x. And I might say this current, the value of this current, it's 5 times I sub x. So the value of this depends on I sub x. It's not independent. It depends on the value of that current. So this current source depends on what? Does it depend on the current here? Yes. Or you might see the same circuit with a dependent current source in it. Just because it's a current source, I might decide the value of this current source, let's call this voltage here, labeled plus to minus VA. And the value of this, it's 4 times VA. Still a current source, but the value of that is 4 times whatever that voltage there. Now, this one is called, I didn't see it in our book, I was looking for it. We call this current controlled current source. Notice this current source is being controlled by what? By that current. This current source being controlled by what? That voltage. So it's voltage controlled current source. It is a current source and it's being controlled by the voltage. This is a current source being controlled by the current. A lot of people say, how can you have a current source and it says 4 VA? That's a voltage. That's just the magnitude, the value of that current source. Instead of saying 6 amp, you calculate that voltage. If this is 10, this will be 40 amps going up. This is controlled by the current. If this is 2 amp, this will be 5 times 2, 10 amps going in that direction. We also have dependent voltage sources, the same as current sources, and some controlled by current and some controlled by voltage. So a dependent voltage source will look like this again. 5 I sub x, just like we did before. But that's a voltage source, not a current. And in this case, again, I can take the previous circuit and just redo the same thing. And this will be I sub x. Or we can, by the way, flip the plus and the minus. I can have the plus on the bottom, the minus on the top. It doesn't matter. I mean, they'll be just backward, opposite. Because we know we can flip either a current source or a voltage source. If you flip the direction of them, just flip the sign. So if I make this minus on the top, plus on the bottom, this will be negative 5x. Again, this is current-controlled voltage source. It's a voltage source that was being controlled by the current. and this is, it's a voltage source that's being controlled by the voltage. So voltage controlled voltage source. But all dependent sources, when we graph them, when we draw a picture of them, we draw that diamond shape. If it's a current, we'll have an arrow in it. If it's a voltage, we'll have a plus minus in it. So I can draw a circuit here. I'll see if I can find something in the back of the book here quickly. Let's take this circuit. So we have an independent voltage source here of the value, I can't see it, but I think it's V3. Some element here, we have no idea what that element. That's V1. We have a dependent current source pointing down, the value of 3V1. We have an element here, we don't know what that is, but the voltage here is V2. And we have I sub 2 here.
Why is that like a square?
We're not telling you what's in it.
No, I know, but the...
Here? In here? We're just saying there's an element here. I don't want to put a resistor. It could be a capacitor, which we didn't discuss. Could be anything else. I just don't want to tell you what's in it. Something attached there. So it says, assume now, note that we need to know something about this problem. What do we know about this? Determine the voltage V1 if. So find V1 if V2 equals 33 times I sub 2. And I sub 2 equals 100 milliamp. Now let's look at this. We don't really talk much about circuits here. I can find all the stuff about this circuit by knowing these two. V2 33 I sub 2. What's I sub 2? 100 milliamp, right? So what's V2 then? It's 33 times 100 times 10 to the negative 3. That's 100 milliamp. Milli is 10 to the minus 3, which is a 0.1. So that's 3.3 volts. I went to the end of the chapter and I took this. Now, one thing about current, notice there's only one branch here. Current is like water. You attach a hose to that hose, the amount of water going through this is going to be equal to that one. They have to be, unless there's a leak in the hose. Well, current's the same thing. If there's no branches, if I don't have any other branch going that direction, like the previous example I did here, that current coming in here is not going to equal to that. It's going to branch. Some will go down this way, some will go in that direction. Then they gather together and they come out at this end. This is equal to that because there's no exit to it. Well, in this case, when you look at that picture, notice this current is pointing down. Well, look at the I sub 2. Where is it coming from? It's coming from here. So I sub 2 is pointing upward in that direction. So what is the relationship of I sub 2 to this current? It's the opposite. They have to be the opposite because there's no other branches. It can't leak. That current going through that has to be the same. So I sub 2 has to equal to 3V1. Can I figure what V1 is? We know what I sub 2. I sub 2 is what? 100 milliamp equals 3 times V1. Can I find V1? It's 100 divided by 3 milliamp, and V1 is going to be 33.3 milliamp. Except I forgot one thing to put what? We said the opposite. Where's my opposite here? Do I have an opposite? I didn't put it there, so I got to put an opposite. This is one pointing up, one pointing down. They're not the same. They're opposite to each other. Opposite means a minus sign. So let me come back and put that minus sign, and now that'll be the correct answer.
How do you have amps for a voltage?
How do you have what?
You have 33 milliamps equals V1.
Correct. The value of this current source, remember, this is a current dependent current source. The value of this is 3 times V1. But it's not a voltage. It's still a current source. It's whatever V1, whatever that number, which is what? We don't know it, but like in this case, look at this. V2 equals 33 I sub 2. This is current, this is voltage. But the value of this voltage source is 33 times the magnitude of this current. That's what that means. Now, if I know V1, I know V3, but we didn't discuss that. They're in parallel. We didn't talk about parallel yet. That's coming up in the rest of the chapter. And there'll be other stuff we're going to discuss. I jumped a little bit here with these, the current going in this direction. We'll talk about them in a minute. So that's what a dependent current source, dependent voltage source, independent current source, independent voltage source look like.